What is it, like $2,000? It probably is. Because the 13 is still what? 1,300? What the 12 are like?
I only get it when the notch comes off.
What?
When you take the notch off.
I think the 12 when I got it was like $1,000. What? Dude, I'm telling you, this Earth wallpaper is where it's at. It literally shows your location.
I was looking, do you have our those scores yet?
I think we did.
I checked that.
Dude, you probably got 100%.
I believe I was supposed to.
On what? Oh, I did. Wait, what? What made you have your copies?
Yeah, 170 over 173. This is the reading question.
Over 170.
These are the reading questions. I didn't do good on that.
I have 102. I have 199 out of 209.
And what's the thing like this?
How do you have less points than I do? Because I have 209.
I think it's like we're looking at a different format.
Then I said 209. That's hard. I got 100.
Tristan.
Yeah, you go. Okay, I need to go 100%. And I got the extra bonus question.
There's a bonus on there?
Yeah. No, it was like named like the muddiest thing. Or something like you don't understand. But I thought you turned that in on paper, didn't you?
Yeah, I think it's right in here.
199 divided by 209, right? There used to be a lot less practice. No, it's at 90. Let's go. I have a 95%. I don't know. You know, it's all fun and games when you see in biology.
Oh, you like write down your stuff?
Yeah, it's mostly
Yeah. You have things for me. All right, let's go ahead and get started. And so I will happily accept whatever assignments you have for me, including late work. And then if you miss the quiz, so quiz makeups, I think that's easiest to either do in lab, so just let me know, or we can do them through the testing center. And so just email me if you missed the quiz, and try not to wait too long. So if you were absent last week, people let me know, and so let's get it made up this week so people aren't taking too much longer. And so for lab makeups, I'm still tentatively doing that midterm week, which I think is week 5. I'm glad you remember. I don't remember my syllabus. So week 5, and maybe that Friday or something, if that works for people. So kind of put that tentatively on your calendar. If you need a lab makeup of 1 through 4, so I'll probably do labs 1 through 4 that day. Maybe 5 if I can't. I think we do lab 5, week 5. So if you need to make up those first few labs, we'll aim for, again, that Friday of midterm week. If this doesn't work for you and you know you need to make up a lab, just let me know. We can squeeze something else in. And so, again, put this on your calendar. And if you need to make up a lab, just send me an email, too, of like, hey, I'm going to need to make up, this lab, just so I at least have a list of what labs we need to do and what setup, so I can tell the stockroom what they need to put out that day. And so I saw that people were doing their reading quizzes, so thank you very much. Don't forget about those assignments. So I'll just remind you again, don't forget reading quizzes. And so again, just make sure you do them. It's just free points for completion. Do the reading, take the quiz, and you can try again too if you messed up. All right, any questions or concerns before we begin?
When is the reading quiz due?
I think they're due technically every Monday, but I still accept them. So it just won't auto-grade them, but I just manually hit yes. So.
Title, like the name of the quiz says due on the 5th, but then I look later.
Yeah, I try to delete all those things, but then there's always errors somewhere, and I apologize. But that's why I don't worry about due dates too much. Just get things in as soon as you can. Just kind of keep up with the pace of the work. I give everybody grace since I know everyone has chaotic lives, and we're still kind of coming off of COVID, so I'm trying to work with y'all. And so other last announcements, so if you are falling behind or having questions, don't forget to either see me, so make appointments with me. So I generally have office hours either just before or after class. And or you can catch me in lab. So a lot of you ask me questions in lab. That's excellent. Just keep asking me questions. We can make outside appointments. I'm available really anytime to try to work with your schedule. And again, in person, over Zoom, whatever you need. And don't forget about the tutoring center as well. And so I recommend Kevin Culhane. He's a prior instructor at RCC. He's working at the tutoring center. He wants to see you. He wants business. So hit him up if you want help as well. And again, he's a qualified teacher, so he'll help teach you the material as opposed to just give you the answers. All right, I think that's all the announcements I had. Oh, and then I handed back some of people's quizzes and I did not get to everybody. So just see me after class, or I will continue to hand them out in lab today. I know some of you were burning to see them. All right, so let's start chapter 4. And again, I don't like your textbook. That's what I'm realizing with these beginning chapters. So just kind of bear with me. I'm trying to respect McCrory's order because that's the book we're following. And so just kind of bear with me as the pieces come into place, I like to say. And so now we're going to look at this periodic trend of ionization energy. And so let's just define, well, what is ionization energy? And so ionization is just the minimum energy needed to remove an electron from an atom or ion in the gas phase. And so this means that it's called an endothermic process. They're just introducing this term a little early to you. And so endothermic just means we're putting in energy into the system. And of course, this also means that we're going to remove the valence electron. And so again, that's the outermost. And so we're going to kind of, at the same time, revisit electron configuration with this, and hopefully they'll build together. And so we're going to start with our first ionization energy trend. And this is, again, the energy to remove an electron from the neutral atom. And so it's most commonly represented by this formula here. And so you just have generic M, so this stands for any atom, and it's going to be in the gas phase. So again, this is a gas phase reaction. And then you have ionization energy, so this is just the symbol for ionization energy. And then you have a 1 here to indicate the first ionization energy. And so again, with that first ionization energy, you're starting with a neutral, and then you're removing 1 electron to create your +1 cation here. And so, i.e. a good example, especially from our periodic table, would be if we're looking at sodium. Do this, not here. So we're looking at sodium. And so let's try to tie things together. So let's look at our periodic table. And I'm going to fill in again the little energy levels of how we fill it up. So remember, this is 1s2, 2s2, so we would fill that up. 2p, so then that would be 6. So let me write that down. So 1s2, 2s2, 2p6. That would lead us to our noble gas configuration of neon. And then our last one, so this is 3s. And this is S1, since we're just filling in 1 electron. And then I went ahead and put our generic pattern up here to kind of remind us that these are always going to be at S1. So again, emphasizing they're alkali metals. They want to lose that 1 electron. That's why they're really reactive. So now we're thinking about sodium. So we're going to write this reaction down. So again, we can represent what we're going to do. We're going to write our sodium metal in the gas phase for this ionization reaction, plus our first ionization energy. So that's going to give us sodium plus that 1 electron, of course, that we just ejected. And then again, we're going to be ejecting that valence electron right there. So there's our valence electron for sodium. So it has 1 valence electron for the alkali metals. So that's getting ejected there. And so now another trend that we're going to look at, and this kind of differs if you've taken Chem 104, we only looked at the first ionization energy. But then in this class, we want to be able to recognize the trends of the second ionization energy and then every subsequent ionization energy after that. And so, again, with our second ionization energy, now we are starting with an M+1 ion. So maybe note that down. So now second ionization, so now we're starting with an M+1 metal. And we're going to do our second ionization energy and give us our M2+ metal plus 1 electron. And so if we were looking at the process, let's just say for magnesium. And so now let's, again, I'll write out the electron configuration. So magnesium's right next to sodium. And we can also write electron configurations in their abbreviated form. And so I'm going to do that now. And so we can write a bracket. This indicates I want the electron configuration starting with neon. And you just start with whatever the previous noble gas is. So now neon is in brackets. And then I can start, okay, starting with neon and 3s2. And then I'm going to go ahead for the alkaline earth metals, put ns2 here. Again, emphasizing that they're all going to be in this whatever ns2 shell, so they have 2 valence electrons. And so if we wanted to write down this process then for ejecting these 2 electrons, we'd have to start with our first ionization energy. And so I'll just start with magnesium plus ionization energy 1. So that gives us magnesium plus 1 electron. And then so we want to eject that second one. I'll just write the electron configuration. So then currently we'd be at neon 3s1 for magnesium plus. Then we can do our second ionization energy. So now that would be magnesium plus whatever that ionization energy 2 is to give us magnesium 2 plus 1 electron. So each time you're just making 1 electron. And of course you could keep going, but we'll look at some trends. And so now this brings us to neon. And so we ejected that electron, so now it's sitting at the noble gas configuration. So let's first look at some trends for ionization energy. And so this is kind of the graph. So again, first ionization energy, so M plus our ionization energy 1 gives us M plus 1 electron for all of these processes. And so we have hydrogen, helium, and then lithium. And then, so what do you notice? So let's first notice which ones are the lowest ones. Which ones always have the lowest energy? So the noble gases are these ones. So with our ionization energy, it's going up, so 0 to 2,000. So these are the highest, right? And so the alkali metals, though, they're all the lowest. And so why do you think that is? Let's start with, what do we say? So let's think about the electronic structure, though, or their reactivity, too. So kind of. So your first statement was exactly correct. So it's easy to pull 1 electron away. But why is it easy to pull 1 electron away from lithium versus neon? Because it can give it up. I don't know who said that, but excellent. Right? Because it wants to. So it wants to get to that full octet rule. And so that's why we say they have an NS1. We also can write their common oxidation state. So it always wants to be in that 1 plus state. And so it's quite happy to give up an electron. Again, it's an endothermic process. It does take energy, but it doesn't take that much energy. It'll give it up. It's, again, happy, so it'll be with the octet rule. And then, so what happens with neon then? It can't, or really, it takes a lot of energy to, and that's because it has the full octet, right? Completely satisfied. And if we're thinking about this, so we also want to, and again, I apologize that Macquarie doesn't introduce orbitals earlier. It's something that drives me nuts. But so for neon, if we think about kind of its orbitals, so we're in the 2p here. So 2p, there are 3p orbitals, so 2s, 1s. And so if I fill in all the electrons, so it has 10 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are all full, and it's happy. So then to create neon plus, again, that's not really favorable. So we have a complete octet. And so then, of course, you would have to break that. So that would be not very favorable, hence why it's high in energy. Then, of course, as you go down the noble gases, you know that energy slightly decreases. So that makes sense. As the radius gets farther and farther out, it has a weaker hold. So the nucleus has a weaker hold on those electrons. So while it still takes a lot of energy, the trend does decrease. So same thing for the alkali metals. So now let's take an even deeper dive into some of these trends. And so we're at lithium. So it goes lithium, beryllium, boron. So lithium, beryllium. What do you notice about boron compared to beryllium in their trend here? So it takes less energy. So that's odd. Because if we're looking, so we're seeing, okay, well, it mainly increases as we go across our ionization energy. And we can write that as a general trend. So ionization energy, so it increases as we go across, again, just in general. And it's going to decrease as you go down. But let's look at what accounts for this little oddity here. And so this is where we want to write our electron configuration. And then we'll also write this little representation of it. So let's draw beryllium. So beryllium, so what would be the electron configuration for beryllium? So 1s2, 2s2. So that looks good. And then let's draw this out as well. So we have 2p. So there's nothing in the 2p yet. 2s, 1s. So filling those up. And so we think about what you would have to do to then make our beryllium plus cation. Right? It would not be that thrilled. Since you have these two paired electrons, you would have to break that. And so that leaves you with this sort of scenario. Meanwhile, let's compare boron and again see what accounts for that dip. So boron then, the electron configuration, 1s2, 2s2, and then now it just begins the 2p, so 2p1. And so now let's draw in our little representation of this, our orbitals. So filling from the bottom. And so now we have 1 in the p. And so we want to compare that. So what happens, which electron is going to be ejected if we hit it with the first ionization energy? The 2p. And so it's actually, we see why it costs a little bit less energy because there's no other electrons in this 2p. So it's just going to lose it. We still have the 2s filled, so it's okay with that. And so that's why if we compare our boron to beryllium dip, that boron is just a little bit lower in energy since we're ejecting that one electron versus ejecting a paired electron. So you're going to have to pay at that price to unpair those electrons. And of course you see the same dip in the next row, so sodium, magnesium, and then aluminum. So aluminum has that small dip again, and again generally increasing. So we can see what also causes this oddity here. So going back, so lithium, beryllium, boron, and then carbon, nitrogen. Now we're at oxygen. So why is oxygen slightly less? So let's compare. So again, we can draw the same thing. So nitrogen, what's the electron configuration for nitrogen? One s2. So 1s2, 2s. So filling it in, 2s. So 2s2, right, because the s can only hold 2. And then that brings us to 2p. So 1, 2, 3. And you could write NP3 here to also help you. We'll come back to this with our Lewis dot structures. So 2p3. And so now we'll write this. Again, comparing what we have to do. So fill in my 1s, my 2s, and then 1, 2, 3. So now I have one electron in each p, and so they'd be quite happy. They're all degenerate. They all have one electron. And so if you wanted to remove one, of course, then you have to remove one of these. So that's not quite too favorable. And leaving us in this scenario. And if we compare oxygen, so now oxygen is just 1 over, so now it's NP4 for its ending. So 1s2, 2s2, 2p4. Now if we compare, so 2p, so now we have 1, 2, 3, 4. And so it takes a little less energy than our nitrogen. Since we have just one paired electron, it's okay with becoming unpaired since you have to pay an energy price to pair them. And so O plus, again, that's why it's slightly less energy. So 2p3, then nitrogen to eject that first electron. So now we bring us over to here. So those are those kind of major trends. And then if you notice, so once you get down to period 4, the transition elements, so we're not going to go through all the weird oddities, but the reason why it's like that is because there's 5D orbitals. They can do different energy levels. If you want to talk about it in depth, I'm more than happy to, but we'll just kind of accept the trends all over the place. But again, generally increasing across the periodic table is what we assume. And so same thing, period 5, generally increasing trend, but some oddities along the way. And so like we're noticing, so the larger the effective nuclear charge on the electron to be removed, the more energy it takes. So basically, right, that effective nuclear charge has to do with how close it is, and then the charge. So as you get greater ion charges, so like a 2+ ion has a greater hold than a 1+ ion, so that all leads to effective charge. But again, the more energy it takes. So that's why we saw the further we got out from the nucleus, then the less energy it took to remove it. So again, write down, you have decreasing ionization energy as we go down. And so again, first ionization energy generally decreases down the group as we move farther away from our nucleus. And our first ionization energy generally increases. But you saw the exceptions and saw how to kind of explain for that. And so this is just a cute graphic representation of first ionization energy. And so you can see some numbers and give you some context. So again, not too much energy difference between nitrogen and oxygen. You can appreciate why. And so now let's look at these kind of successive ionization energy trends. And so these trends just depend on the number of electrons, or valence an electrons an element has. And so removal of each successive electron costs more energy. And so this applies, so think back to even our magnesium case. So magnesium, it wants to be in the 2+ oxidation state, but even then it just still requires more energy to remove that second electron. And you're also thinking about the effective nuclear charge. So once you remove that first one, now you have that M+1 ion. So it's holding on just a little bit tighter to that electron. And so again, it costs a little bit more for that second ionization energy. And then so the other thing that we'll want to recognize is where do you have the large increase in energy when core electrons are removed. So that is also kind of telling us that there's some sort of shell structure when we see this. So this is kind of a hint at shell structure. And this is, again, where McQuarrie and I kind of differ in our teaching methods. McQuarrie kind of is trying to bring you through the discovery of, like, look, you were doing these experiments and you're seeing these observations. Like, this is how you would interpret the orbitals then. But I want to, like, just give you the answer. Like, these are the orbitals that we know, and this is why. So different styles. And so the other thing, I'm pulling up your book as well for this, because sometimes I think your book makes easy things look really complicated. And so what I mean by that is if you look at these little logarithmic graphs, it may be hard to appreciate what you're looking at initially. And so all this is saying is they're graphing the ionization energies, in this case, of lithium. And they changed it to the logarithmic scale because, as you're kind of seeing with these values, they're pretty large. And so they took the log of them to make them easier to visualize. So we're looking at the log here. But what you want to appreciate is, well, why is it for lithium you have this huge energy gap between the first and the second? So you notice you have a jump from 1 to 2, and then 2 to 3, you know, it's increasing, but it's not a huge jump. So what accounts for that? And so let's look at other trends. So now if we look at beryllium, so now we notice we have 1, 2, and then the jump. And so what do you know about beryllium? So how many valence electrons does beryllium have? Can you show me fingers too, or do you have an answer? 2. And let me flip back to our periodic table. So it has 2 valence electrons. And so if we're looking at this, okay, that's kind of matching with this pattern, is you have 1, 2, and then once you try to remove that next subsequent one, so now this is no longer a valence electron. Right now that would be considered more your core electron, and so it takes a lot more energy. And so your book just continues this, showing you all at least the first row. So now for carbon, we can kind of see this. So how many valence electrons does carbon have? So 4. We could flip back. Okay, 4. And then so looking at your book, so 1, 2, 3, 4. So now these are all the valence electrons, and then that big jump as we remove that first core electron. And so another one, just to look at these graphs and understand them. So now we have neon. And so neon, we have this clustering of 8. And that makes sense. Neon's our noble gas. It has 8 valence electrons. And so we have our big jump between the 8 and the 9 as we go down and start ejecting those core electrons. So that's kind of the graphical representation. And so here you can see it on a chart as well, so you can get the numbers now. So again, following that same pattern, so we have sodium. So sodium, 1 valence electron. Now I'm going to go ahead and write out our Lewis dot symbols. And so all the alkali metals, again, they have just 1 electron. We want to represent that NS1. Oh, I shouldn't have written that there. Let's write it here. NS1 for alkali metals. And so again, you can see that represented by this big jump. So of course, this first one gives you sodium plus. And now once you get to here, we're in the core electrons. So sodium 2 plus. And now we're in core electrons. So you can kind of draw it like that. Well, you probably wouldn't be asked to do Lewis dot structures of this. And so again, busting into that core. So magnesium, I would draw like this for its Lewis dot structure with 2 dots on the side. So NS2 following that. Again, that jump. So aluminum, same thing. So now it's NS2, P1. So our large gap as we go down to our core. So silicon, 4 valence electrons. So same thing, huge gap. So silicon, we can write phosphorus at 1, 2, 3, 4, 5. And so you can kind of, what you might be asked to do in an exam as well, if you were given, let's just say you were given these values for phosphorus and they weren't labeled, you just have, okay, I have successive ionization, energies 1, 2, 3, 4, 5, 6, and 7. And then you want to identify where is the jump. And so for this case, here's the jump from 5 to 6. So that means it has 5 valence electrons. And then once you eject that 6, again, you're going into the core. And so you see this pattern repeated. So sulfur, 6 valence electrons. Again, there's a jump. And then I don't have all the values for chlorine and argon, but of course they would have the jump at 7 to 8 for chlorine or 8 to 9 for argon. So any questions about ionization energies so far? All right, so now let's look at our Lewis dot representations. And we can tie these again to our electron configuration. So that's how we should look at them. And so the way that I always like to think about it is you have whatever your generic metal is, and then it doesn't matter which side is which, but I kind of think of them as one side is going to be your valence s orbital, and then the other 3 sides are your 3 p orbitals. And so that way you can just take your electron configuration and essentially translate it to this Lewis dot structure. You also see that it really repeats the pattern, and so once you know what each group, what their Lewis dot structure, or it's also called electron dot, so you don't get confused. But you'll find that all their Lewis dot structures kind of repeat. And so let's start again with our first group here. So our S1. So of course there's hydrogen. And it doesn't matter which side you put the dot on. You can put it on the top, on the side. I don't really care. And then so for helium, I like how your book draws it, so I agree with your book. So helium, you should draw the 2 electrons on the same side. And so helium, remember, is technically in the NS2 category. And so anything else in that category, like magnesium, so I like your book, how it draws it. So magnesium, it should be 2 electrons on the side there. Again, representing that you're filling up that s orbital first. And so why I emphasize that is that you will see other textbooks where they draw magnesium like that. I don't like that just because it doesn't mean anything. It doesn't correspond to our orbitals. And, you know, again, you may have learned this way in high school chemistry, but it doesn't truly represent our atomic orbitals. I don't like it. And so I'll point out some other oddities. So beryllium's good. Boron is fine like this, so I prefer that it's drawn like this just to represent its Lewis dot, or its electron configuration. So again, 1s2, 2s2. So we want to represent those 2 electrons there. And then boron, so 1s2, 2s2, 2p1. And so I like that 1 electron there. Although some people could argue that boron does a 3 thing. So boron tends to make 3 bonds, so it kind of tends to hybridize, but this is preferred. And then carbon, I'm honestly surprised your book wrote it this way. So this way it would represent our Lewis dot structure, so 1s2, 2s2, 2p2. And then when you fill up the carbon, so don't forget with the p's, so I'm just going to show the valence electrons for carbon. So you fill 1, 2, and then you want to put an electron in each p orbital before you go back and double it. So I like that they did this. That's fine. But you may also write carbon like this. And it is the only group 4 that is appropriate to write like this. And the only reason why is that carbon tends to hybridize. And we'll go over this later, what that means in detail. But essentially, carbon wants to make 4 bonds. It always will make 4 bonds. So this is a better representation of its reactivity. However, for like silicon, for example, so silicon, where can I draw silicon? Oh, they drew silicon. So silicon, I like this. Although it is unstable, it can be isolated as a 2-coordinate compound, so kind of reflective of this. So it's okay. It doesn't hybridize as readily like carbon. And so going across, and you could also write this on your periodic table for notes. And again, if you need a second copy, I'm more than happy to give it to you. But you could write, you know, your generic examples at the top for each group. So aluminum, 1, 2, 3, and then I'd put silicon for our representative atom. And so just going along, so now let's look at group 5, what that looks like. And so they all have this sort of form, so that should represent, again, their electron configuration. So if we look at this group, they're all going to be NP3. So NS2, NP3, just kind of writing that generically. And so again, that's why it's written in this form. So it should follow our valence electrons, oops. So filling the S first, so it's lower in energy, then putting 1 electron in each P. And so that gives you that 1 lone pair and then 3 lone electrons. And so again, this is showing us the reactivity is phosphorus. It's going to tend to make 3 bonds. And then once it does that, it's still going to be reactive. And so this is super reactive, but then those 2 lone pairs can then go on and react and do other things. And so we can write our generic. I'll just write nitrogen. Again, doesn't matter which side it's on. I just wrote it like that.
Can you go up to the top, where you drew your circle? Keep going. That's.
Marissa, did you say it doesn't matter which side the S?
Yeah, so I don't care, like you could write nitrogen like that. You know, orientation doesn't really matter just for these Lewis dot structures. And then you'll kind of see how to start piecing them together, but that'll come. So now here's oxygen. So our group 6 representative, so NS2, NP4. So again, filling up our s orbital first, and then 1, 2, 3, 4. And so you see that's how we get 2 lone pairs of electrons, and then 2 lone electrons prime for bonding. And again, you can write it any orientation. So I usually like writing the 2 dots next to each other, but it doesn't matter. We'll write our representative. And of course, our last one, so fluorine. So generic NS2, NP5 now. So 5 electrons in that P. So now you just have 1 little lone one. And so this means fluorine likes to make 1 bond as well. So let's draw our generic halogen example. So 1, 2, 3, 4, 5, 6, 7. So again, just 1 lone electron ready to bond. And then, of course, anything with a satisfied octet is going to have 8 electrons around it in your NS2, NP6 form. And so now we can clearly see 8 electrons. And not too many other ways you can draw 8 electrons around it. Of course, argon's the same. Potassium. And then just be expected to write Lewis dot structures for either cations or anions. So if you had like potassium plus, so you could start with neutral potassium, remove 1 electron, and you could either just write Ka plus like that, or if you wanted to write in all those, I would be okay. Either way, you're showing that it has an octet. And so let's just say we had sulfur 2 minus then. So we could start with, of course, the neutral sulfur. And then sulfur 2 minus now has 8 electrons, and you just, again, write your charge on there. So just don't forget your charges on your Lewis dot structures of any ions. All right, questions over this? Hopefully electron configuration and Lewis dot structure are kind of helping each other. And then hopefully you're kind of seeing the pattern forming, and then again the pattern with filling in electrons. Ask questions. And so now we're going to kind of take a step back for a second. And so we've been looking at all these electrons, but now we just want to take it back to really simple and just focus on the hydrogen atom for a second. And your book is also going to take you through, well, how do we discover quantum mechanics, kind of what happened, what was going on, what was the historical context. And so we're going to try to look at some of the strange phenomenon that they were observing and why they had to turn to quantum mechanics. And so early 20th century scientists began investigating the small world of matter, or quantum. And of course, a lot of these people were all working together. So Einstein, Niels Bohr, de Broglie, Max Planck, Heisenberg, Dirac, and Schrödinger. And so all of them, of course, started our understanding of the subatomic level, so electrons, protons, neutrons, but really also the quantum structure. And so this is where all those s, p, d orbitals all come into play, how they started discovering them. And so they found that absolutely small matter behaves much differently than matter of the macroscopic. And so we'll look at these experiments. So some things that they started noticing were these wave-particle duality. For example, they noticed that the electron sometimes behaved as a particle and sometimes behaved as a wave. So this was really confusing. So they had this wave-matter duality concept. And so also the difficulty in studying this is, of course, electrons are incredibly small pieces of matter. So the number of electrons in a single speck of dust is higher than the number of people who have ever lived on Earth. That's pretty crazy. And so directly observing an electron in an atom is impossible. So trying to observe its changes are difficult. So even if you shine a light, and this was some of the problems with the early experiments, is that as soon as you shine a light on the electron, now you've already perturbed it. And so the quantum mechanical model explains to us how electrons behave. And so it gives us how it's light in nature and not the particulate characteristics of the electron that dictate the chemical and physical properties. And so we can't just view it as a small piece of matter, but really a cloud of most probable positions. And so this is where your s orbitals come into. It's like this is our probability density map of where we can find an electron. We don't know exactly where it is in this cloud. We just know it's somewhere in there. And of course, this quantum mechanical model is going to tell us everything. So now we're going to get those trends. So we're already seeing that as we look at the explanation of the s and the p orbitals. And again, all those little ionization energy trends. But this gives us a greater understanding the behavior of elements. So again, you can do back of the envelope calculations on relatively complex systems and get a decent guess of what's going to happen. And colors and atoms. So this is more difficult to do back of the envelope, but we will still do it. And again, for hydrogen. And so it also helps us predict which elements are metals and nonmetals, why elements gain 1 electron and others gain 2, and of course why some are reactive and others are inert. So let's start back now at light. And so light is a form of electromagnetic radiation. And so all that means is that it's composed of perpendicular oscillating waves, one for an electric field and one for a magnetic field. And so here's kind of a pictorial representation of that. So you have your electric field component and your magnetic field component, all going in that direction of travel. And so a really key point is all electromagnetic waves move through space at the same constant speed. And so write this down somewhere if you need to. So 3.00 times 10 to the 8 meters per second. So that is our speed of light. So that will be important in our calculations in this chapter. Let everyone copy that for a second. And again, these electric and magnetic fields, so they are going to be perpendicular to one another. And so before we even understand how to look at these experiments that they were doing, we have to understand how we characterize a wave. And so a wave can be characterized by the amplitude. So this is going to be the height. So you either measure from the base to the top here, or you can measure from the base to the bottom. This would also be the amplitude. And so again, distance from node to crest or node to trough. So node just being this point, so your base. And the amplitude is a measure of light intensity. So the brighter the amplitude, the brighter the light. The next way we can characterize our waves is, so waves always have some sort of wavelength, so given by the symbol lambda here. And so your wavelength is either going to be crest to crest or trough to trough here. So this is also the wavelength, so they would be the same. And so wavelength, usually, it's either going to be in nanometers or meters. So just watch your units. So you'll notice with the electromagnetic spectrum, it's usually all in nanometers. And so a lot of the calculations tend to be in nanometers. There's going to be a lot of converting back and forth. And so wavelength and amplitude are also independent properties. So of course you can adjust your intensity of light. And then the wavelength of light determines its color. So wavelength gives us our color. So we change the wavelength. So a long wavelength is going to be associated with something lower on the spectrum. Let's see. I have a picture of the spectrum somewhere. There it is. So we go to the next page on the notes. So red, these have the longer wavelengths. So are you all familiar with Roy G. Biv for Colors of the Rainbow? Excellent. I had a class where everyone looked at me like I was crazy when I said Roy G. Biv. So you never assume. So I like to keep it in this order so then we know who has the longest wavelength. So red over here, they all have the longer wavelengths as we travel across. So notice how tiny too the visible region is. So it's only from 750 nanometers to 400 nanometers. And so 400, that's going to be shorter, and that's what gives us the violet. And of course, everything else in between. So again, our wavelength determines our color. And so the color of light is determined by its wavelength or frequency. And so white light is a mixture of all the colors of the visible spectrum. And there it has Roy G. Biv. So you can take a prism and it'll take white light and spread it out into the spectrum. We're also going to do some experiments. I want to say it's next week, where we're going to look at the atomic absorption spectrum of different elements. So we have cool neon lamps, and then you'll take the special spectrophotometer, and it essentially gives you kind of the rainbow or for your elements. So we'll learn that different elements have characteristic wavelengths. But if you take a spectrophotometer, and you'll practice with this in lab, you'll hold it up to the light, and you should see the whole rainbow in the light. And so when an object absorbs some of the wavelengths of white light and reflects others, it appears colored, and the observed color is predominantly the color reflected. So if you have a green object, that means that it's absorbing the opposite, so red. And so what are the characteristics of energy? So we also have frequency, or nu. So usually it's like the little curly V looking symbol for frequency. And so frequency is defined as the number of waves that pass a point in a given time. And so this is going to be per second. So over second, or hertz would be the other way. So again, same thing. And so our total energy is going to be proportional to the amplitude of the waves and their frequency. So of course, the larger the amplitude, the more force it has, but then also the more frequency those waves occur, then the more force you have. So if we go back to our little electromagnetic spectrum, you can see, so we have low frequency on the left, high frequency on the right, and we can see what corresponds to that. So X-rays, we all know X-rays are not that good for you, hence why you go to the dentist and they put a lead garment to protect all your reproductive organs. And then, of course, gamma rays, those are what cause destruction. So that's super high frequency and high energy destruction waves. And so again, violet is also going to be the most energetic, comparing our electromagnetic spectrum. And so now we want to know the relationship between wavelength and frequency, especially the mathematical frequency. And so if you have a long wavelength, that means you're going to have a lower frequency, right? These points are going to be hitting you less. Meanwhile, if you have a shorter wavelength, that means you're going to have a higher frequency. And so mathematically, this is given into frequency is the speed of light divided by wavelength. So then that gives you meters per second divided by meters, which gives you the unit of 1/second, which corresponds to your frequency. So that all checks out. And so I would write this formula down. And since the speed of light is constant, if we know the wavelength, we can find the frequency, and vice versa. And so let's see if we can do a practice. And so that's what I was saying, is there's a lot of conversions. So it's asking, calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14 hertz. So take a minute or two, see if you can set it up, punch it into your calculator, and then we'll see what everybody got. So we can set up our map. And with this one, you could always rewrite it in the triangle trick form too to help you out. And so we're trying to find wavelength. So I'll cover wavelength. So that means I should probably take the speed of light and divide it by the frequency. And so 3.00 times 10 to the 8th meters per second divided by my frequency. So second goes on top, 4.62 times 10 to the 14th. And so that'll give us meters for our unit. Oops. Sorry, I forgot to pull out my calculator. So 3, and make sure you use like the E button and everything. So that means times 10 to the 8th. So divided by 4.62 times 10 to the 14th. And so do we get this number when we punch it in? Are you looking for the E button? If you have this version, there's a little E there. If you have another calculator, I can help you after class. Make sure that you get this number. So this is in meters, right? So we're not at the quite correct answer yet. So 3 sig figs, 3.49 times 10 to the negative 7 meters. And so I want to go to nanometers. And so let's just show our conversion explicitly. So 1 nanometer So 1 times 10 to the 9th nanometers is equal to 1 meter. So meters cancel. So multiply those times 10 to the 9th. And so you should get 649 nanometers. And then you can always do a little sanity check. So 649, yeah, that's about in the red region, and we're in the colored region at least. And so everything makes sense with our sanity check. And so we can feel pretty good about our answer, 649 nanometers. So any questions on this? Oh, so this is just our conversion factor. So nano, if you look at what a nanometer is, it's like 1 times 10 to the negative 9, but that's times the base unit. So what it's saying is 1 nanometer equals 1 times 10 to the negative 9 meters, which you could use this as a conversion factor. I just personally don't like negative numbers. It doesn't matter, but I don't want to accidentally drop them when I'm plugging them in. So I just picked a positive conversion factor, multiplying everything by 1 times 10 to the negative 9. Did that clarify that? Other questions about this? And so now we can look at our electromagnetic spectrum. And so again, we have our low frequency to high frequency, and this means we have low energy. So things that are considered low energy are going to be radio waves. And so if you look AM waves, so AM waves tend to travel longer distances, and so they have a long wavelength. And then you have TV, so FM cell. I forget where 5G is. So 5G is kind of odd since 5G is a really broad term, so then you have to start looking into exactly which frequencies they're talking about. Again, closer to like the microwave range or so. And then moving over, you have infrared, so IR. And then, of course, continuing to the visible. Ultraviolet is, of course, right next to violet. And now we start getting into kind of the high energy and more destructive ways. So, of course, ultraviolet can cause mutations in your cells, but it also breaks down chemical bonds, and sometimes slowly. Of course, that's why things eventually degrade in the sun. And, of course, X-rays and gamma. And then comparing wavelength. So these are extremely long wavelengths. And again, those long wavelengths too, those are better for traveling long distances through buildings. So part of the problem with 5G, and I don't think they're talking about 5G enough in this sense. So 5G waves, since they're so much smaller, they need to have more repeaters. So I don't know if you saw this happening, but as they've been expanding the 5G network, they have to put little boxes everywhere so the signal can go, because like I said, those short waves have trouble traveling through buildings and they can't travel as far, so you have to have a lot of repeaters, so it's more infrastructure. So I'm not that crazy about 5G, not to mention the studies about 5G, but any sort of radiation studies are always confounding. But anyways, you can always research that. And so visible light is a range from 400 to 700. And so very small fraction of the entire electromagnetic spectrum. And so shorter wavelengths, high frequency lights have higher energy. So radio waves have the lowest and gamma, again, have the highest. And like we've been discussing, those high energy electromagnetic radiations, those can all damage biological molecules. And so what happens when an atom absorbs energy? And we can see this in both the form of fireworks and neon lights. And you're going to see this in the flame test and the neon lights in next week's lab. And so an atom or a molecule absorbs energy. That energy is then released as light energy. And so what you're kind of thinking of, and we're getting there, and just we're thinking about it really generically right now, is we have our valence electron, so it's here, in whatever the outermost shell is. And then it absorbs some energy, so that means that electron gets promoted somewhere. And so it depends on how much energy it's given, so it's promoted to some energy level, could be the next one, could be several up. And then what you see, so it's high energy, and then it's going to relax back down to the ground state. And this relaxation, so that energy that's given off, that's what you're seeing. So you're seeing that light energy from whatever transition. So it corresponds to, again, some electron going from a high energy level back down to a low energy. And so that's what gives us pretty colors with the fireworks. And there's also magnesium in there, so magnesium gives it that really, really bright glow. But then there's also, fun colors in there, generally transition metals that give off cool colors when you give them a bunch of high energy and burn them. So same thing with neon lights. We'll see that with our neon lights. So again, you just pass an electrical current that's going to start promoting some electrons to higher energy levels. They're relaxing back down, and we get a pretty color. And so then you can take that emitted light. So you have your neon light. It might look orangey if it's neon. And then you pass it through a prism. So then you're separating that light into its separate patterns. Then you get what I was talking about, the absorption spectra or emission. So you have a pattern of particular wavelengths of light that is unique to that type of atom or molecule. And so emission spectrum just means that it's going to be kind of showing you the lines And so sometimes you'll either see emission or absorption. And kind of depending on how it's presented, either you're seeing the lines that are present, or those same lines would be kind of faded out where they're not present, where it's showing you the absorption. And so again, you'll do this in lab next week. So you'll have your lamp source. So we'll have hydrogen, helium, and probably like argon and neon or something. I'll see what they put out. And then that's what I was talking about with that spectrophotometer, is that you have your slit that you'll look at your spectrophotometer with. That light will go in, and then it separates it. So there's a little prism in there that separates it out into the spectrum. So that's what you'll try to observe for yourself. And so hydrogen is relatively simple. So it has 1, 2, 3, 4 lines roughly. And so hydrogen is the simplest. It just has 1 electron, so you can think about that corresponds to at least 4 different promotions. There's 4 lines. And you'll find that it gets pretty complex pretty quickly. So here's an example. So helium is starting to get more complex. Barium, so now more lines. And then if you compare, so again, this is technically an emission spectrum where you're seeing the colors, or you'll sometimes see this absorption spectrum where again, those same bands that you would see with the emission are now faded out. So there's neon. And again, now neon is looking pretty complex, and you'll get a chance to observe that for yourself, just how difficult it is to look at these lines. But why is this useful? So going back to elements have their own unique spectrum, so we often say it's kind of like a fingerprint of that element. And so especially now, as the new telescope brings back even more pictures from outer space, so scientists can apply different filters to the camera, so they take a bunch of different photos with different filters and everything. And then from there, they can see the unique spectrums that are in the pictures and then identify all the elements through their spectrum. So that's how they can identify what's in space. And so we'll go back to kind of the Bohr model for a second. And so if we remember the Rutherford model, so that was our plum pudding. So our plum pudding, or even just having a nucleus, so even if we go to the simple, we have a nucleus and we have some sort of electron, right? This does not really explain these structural changes that occur when an atom gains or loses energy. And so with this, Bohr was kind of trying to develop a model. And so he kind of came up with the first ideas of energies being quantized. So his major idea was that the energy of the atom was quantized and that the amount of energy in the atom was related to the electron's position. And so quantized, again, meaning that it has very specific amounts of energy. And so this is coming from kind of these line spectrums. So again, you have 4 distinct lines. So we don't just have a whole spectrum of colors. It's really discrete lines that he's thinking correspond to, again, specific transitions. And so this is, and honestly, we still kind of use this model today, especially, I like this picture, especially, you know, in like intro chem. So he just has this very basic level of our n equals 1. And again, we can correspond. We know that means that's our 1s2 shell. So this is our first shell. Fill that up. And then n equals 2 corresponds to your next level, so where you have S and P. 3 corresponds to now S, P, and D is allowed. And 4 would be S, P, D, F, etc. And so we can, again, only really look at it for hydrogen. Otherwise it gets too complex. So we're just looking at these basic energy levels for hydrogen. And so all we're saying is each line on the spectrum corresponds to a transition here. And so we'll do the math, probably not today, but Thursday. But just looking at this, so if you have a transition from n equals 5 to n equals 2, so you could find that that would correspond to 343 nanometers. So again, very specific wavelength, and that electron relaxing back down would give you that pretty color. The blue-green is given by a smaller transition, so 4 to 2. You can see a little less energy. And then red, so lowest energy, and then corresponds to our smallest transition, so 3 to 2. And so energy is also defined as being negative, and so the electron's energy is lower, made more negative as a result of this interaction with the nucleus. And so an electron has an energy of 0 when it escapes the atom. And so as n gets larger, the following occurs. And so this corresponds with our other energy levels. So just like we've seen before, the subsequent gap of 1 to 2 is the largest, and then they get smaller and smaller and smaller. And of course, we have n equals infinity. And so n equals infinity, this is again going to be your escape energy. And so we have this relationship, so energy for each level is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n corresponds to your different energy levels, so 1, 2, 3, 4, 5, so just discrete numbers. And so you can appreciate from this graph, so some of these transitions are going to be too high energy, so we wouldn't see them. So there are a lot of potential allowed transitions, so again, hence why the absorption spectrum gets really complex really quickly. So again, we're just looking at hydrogen, where it only has 1 electron, but these are all the potential things it could do. So we have all of the ultra high, or excuse me, the high energy, short wavelengths, so ultraviolet energy. And then we again have our 4 visible wavelengths corresponding to those transitions, and then you would have others that are even lower in energy than that red, corresponding to infrared wavelengths. And so you can see those are kind of smaller transitions among like the middle levels. And these are just all what's allowed, basically. So you would have to think of all the possible combinations of, you know, your electron going 4 to 5, 5 to 3, 5 to 2, 5 to 1, etc., to give you all the possible scenarios. All right, that's probably a good place to stop, and we're out of time. So we'll pick up with the history, and there'll be more math. So we'll do more math practice on Thursday. And then if you want your quiz, I'll try to grab you. And I will end this recording.